example 2, 8.4 for 30-1 math, we start to solve exponential equations with logarithms because when we looked at solving exponential equations 7.3, one of the main requirements for that was we had to be able to write them as the same base. The problem here is 4 to the power of what is equal to 605. And it is not a rational number. So it's very difficult to just magically come up with, the number that you would have to put in the exponent on 4 to get 605. So instead, what we do is we work that log form, and I'm going to write it one more time up here, that if the log base 10 of x is equal to the log base 10 of y, then x is equal to y. Now, that's true in either direction, if you want to talk about that. So really what we have in this example is, and I'll write it underneath, that if we have 4 to the power of x is equal to 605, then log base anything. And that's really important, that as long as those two bases are the same, and valid, so you can't have 0 or a negative in there or anything in high school, they're true. Now, that makes it kind of easy to solve it a specific way, which would be to introduce a log base 4. If you introduce log base 4 on both sides, you just get that x is equal to log base 4 of 605, which is the answer. But I think a better technique is to introduce a log base 10. And the reason for that is because log base 10 is doable on any scientific calculator. And if I introduce a log base 10, what I get is that the log base 10 of 4 to the power of x is equal to the log base 10 of 605. Now, that might not seem like it's a big advantage, but we're just working that log form in the other direction. The reason why that is an advantage is that we can solve this because one of our log laws, the exponential or the power log law commonly called, allows us to manipulate this x out of the exponent. And so that's the first step that we do. We use our power log law to say that x times log base 10, because it's not written, of 4 is equal to log base 10 of 605. And now, because log base 4 is a number, right? It's whatever exponent I would need to put on 10 to get 4. So, between 0 and 1 for sure, we can treat it as a number. So I can divide both sides by it. And what I get is that x is equal to log base 10 of 605 divided by log base 10 of 4. All right, I'm just going to pause the video for a second here. Somebody's coming into my room. Okay, sorry about that. So in that current form, that's enough for an answer. That's the exact form of that answer. And it is important that because the question says, what accuracy is required, this is why I like log base 10, because now I can type that into my calculator. The one thing that I want to put up here on the board is that when you do put it into your calculator, if you're using the Texas Instruments, will open a bracket as soon as you hit the log button. That means that when you type in log 605, you need to close that bracket, then hit the division symbol. Again, it'll open the bracket on the 4, but because we're not doing anything after log base 10 of 4, you can just leave it like that. But again, if you're a perfectionist, you can certainly close that bracket as well. And when you do that on your calculator, what you get is a very long and non-repeating decimal, but it asks us to round it to the nearest hundredth, 2 decimal places. So I'm just going to put that I get that x is equal to 4.6203. Maybe I'll just move this out of the way. Oh, of course, it's not going to go together. There we go. Because it says to 2 decimal places, 4.62 would be what we were looking for. All right, not that bad of a question. They do get worse. I mean, I don't want to make it seem like they're not solvable or anything like that, but they do get a little more complex, and they kind of see, you'll see in B and C that they get more complex as we go. So B wants us to solve 8 times 3 to the power of 2x, I'll throw a bracket around that like they did, is equal to 568. Now, again, there's a couple different ways of solving this. I really like the idea of getting the variable and the exponent alone on one side. So how I'm going to solve this is immediately, I'm going to divide it by 8. Now, one of the reasons why I like to do that is 568 is a multiple of 8, which is sometimes difficult to see. But what I end up getting then is that 3 to the power of 2x is equal to 71. I have no idea what exponent I would put on 3 to get 71. I know it's in between 3 and 4, but that's not useful. So we are going to continue to exploit that log form because it does allow us to solve for when the variable's in the exponent. So I'm going to introduce a log on both sides. And that's a really important concept, that the logarithm is an operation like any other, like multiplying by 3 or like taking the square root. So as long as we do it to each side, that's a valid operation. And the inside of the argument of the logarithm must always be positive. So you cannot introduce a log if you have -5 on one side. All right, to solve this, I'm going to use my power log law. and I'll write that power as a bracket. So 2x times log 3 is equal to the log of 71. Just draw an arrow there. What I'm going to do then is I'm going to divide the left-hand side by everything but x. And I'm going to write that on this example, that 2x log 3 divided by 2 log 3 is equal to the log of 71 divided by 2 log 3. On the left-hand side, the 2 factors will cancel and the log 3 factors will cancel, and I'm left with x is equal to the log of 71 divided by 2 times the log of 3. Very, very important that you're careful typing this into the calculator. Again, I'm going to write that calculator step underneath. You should do the log of 71, close that bracket, then divide it by, put a bracket around the numerator or denominator, sorry, because it is more complex than just a variable or just a number or a factor. You want to make sure that your calculator doesn't just divide by 2 and then take that result to multiply it by log 3. Please do check that you can get this value on the calculator. It's no use just kind of making sure that you can, see what I'm putting on the board. You need to make sure you can do this final step as well. And what I get is that x is equal to 1.94 with a bunch of zeros, and I'm going to write the whole thing because I have room now. So 1.9400292217. That decimal does carry on. It's irrational. Never repeats, never terminates, and so you really should, I like indicating that with the 3 dots there. But because we're rounding to 2 decimal places, x is equal to 1.94. Now, I should mention that because this question is round to 2 decimal places, there's another way of doing this. It's making y1 equal to 8 times 3 to the power of 2x, making y2 equal to 568, and solving for the intersection. That will work. The problem is it will never give you the exact form answer, and we are going to push that exact form answer more and more because it shows you can use the logarithm. And fortunately, C is really as hard as it gets. And it is difficult. There's a lot of manipulation required. Again, importantly, the 7.3 technique fails. You cannot write 3, or easily you cannot write 3 in base 4 or vice versa. So we are going to immediately, because we have a single base on both sides, I'm going to introduce that logarithm. And as we work with logarithms more and more, it is useful to remember that it allows us to make exponents coefficients. And that's ultimately why it's so useful for these exponential equations, because on the left-hand side, the base 4 inside the argument of the logarithm, so right here, is all to the power of 2x minus 1. So the entire exponent 2x minus 1 is now multiplied onto log base 10 of 4. And the same thing happens on the right-hand side. These brackets are very important. I have seen phenomenal math students just, pretend that they don't need them and then forget that they should have been there. So it's very important that you're systematic with that notation because it prevents a lot of mistakes, because the next step is that we have to distribute log 4 onto both terms. So I get 2 times x times log 4 minus the log of 4 is equal to x log 3 plus 2 log 3. Now, this immediately looks really complex. All of a sudden, there's 4 logarithms. But I always, struggle with the idea that students, log 4, log 3 is a constant. They are equal to some number. It's just such an ugly number that it's better to write it as log 4. So I would like to point out that this could be thought of as 2x. Well, I'm not going to use the same coefficients because I think that's going to make it look more confusing. But let's say I gave you 6x plus 7 is equal to 10x, I don't know, minus 3. Just some random equation. You would likely group the terms that contain the variable. So probably subtract 6x from both sides. Say that 7 is equal to 4x now, minus 3, add 3 to both sides, and then finally divide. Now, it is very important that we are doing essentially the same thing. It's just then instead of 7 or negative 3, we have these logarithmic terms, these log terms. And so what we're going to do is the same technique, which is I'm going to get all my terms that have an x on one side. And then I'm also going to get all my terms that don't have the variable on the other side. Now, by using these additive inverses, just like classic algebra, x log 3 minus x log 3 is 0, so they cancel. Negative log 4 plus log 4 is 0, so they cancel. And what we have is 2x log 4 minus x log 3 is equal to 2 log 3 plus log 4. Like I said, this question is certainly a little bit trickier. There's much more manipulation. Where we really are at this point is right here. And it's important that what we did in our classic algebra is we divided by 4 because it isolated x. In order for us to see what we have to divide both sides by to isolate x, we have to factor x out. And when I factor that x out, I'm left with 2 log 4 minus log 3 is equal to 2 log 3 plus log 4. Right-hand side hasn't changed, but, and this is certainly a tricky last step, on the left-hand side, our variable is multiplied by that bracket. So we are going to divide both sides by that bracket. And what that allows us to do is on the left-hand side, the bracketed expressions cancel. 2 log 4 minus log 3 divided by the same thing is 1. So we have 1x is equal to, and on the right-hand side, we are left with this mess. Now, you could certainly use your log laws to condense this just a little bit, and we typically don't push that a lot in 30-1 math. What we want to make sure that you can do is come up with the exact form, and I'm going to write it for this question, that this is exact, that is the perfect answer, but because the way this question is worded, it wants us to find to the nearest, I think it was nearest hundredth, right? 2 decimal places. And I want to write down those calculator steps. This is going to be equal to, in a bracket, 2 times the log, it opens a bracket, so we need to close it, plus the log, again, it opens a bracket, so we need to close it, and then we bracket the numerator. So I bracket it around the entire numerator, and then when I divide, I'm going to bracket around the entire denominator as well. And one of the hassles in this unit is that you have to get used to the calculator entering, because it's really important that you be able to get that actual, decimal answer as well. And make sure that you can get the same thing that I do. I'm going to put that into my calculator right now. You know what? I don't know why I'm not. I'm just going to fire up my calculator emulator because there's no reason for me not to do this with you. And we're going to type that in. Really, really important to be careful with those brackets and make sure that we're looking at them carefully. And so we're going to type in with a bracket 2 times the log. See how it opens that bracket for us. There's a 3 inside that logarithm. I'm going to add log 4. Close that bracket around the entire numerator. And then I'm going to divide by my denominator. And I just need to steal a look at it. So it's 2 log 4. So a bracket around the denominator, 2 log 4 minus the log of 3. And I'll close the bracket around the entire denominator. Make sure I double check so I don't screw it up. And then when I hit enter, I get that answer. 2.140722. Now, I talked about that other technique or that other way of solving things, and that would be to just type in the original equation into our calculator and find the intersection. So I think it's important to see that technique as well. So we're going to kind of verify with that. And the way that I'm going to do that is I'm just going to type in the original forms into y1 and y2. So my original left-hand side was 4 to the power of a complex exponent, so it needs to be put into a bracket. My right-hand side was 3 to the power of, again, we need a bracket around that exponent, and it was just 3 to the power of x plus 2. Now, you never really know where your answer is going to be. I don't expect you to be able to eyeball the solutions to exponential equations. So I typically start on Zoom Standard, and then if I don't see an intersection, I'll switch my window settings after that. So there's my left-hand side, 4 to the power of 2x minus 1. Here's 3 to the power of x plus 2. It's in red there, slowly graphing. And, it might not be clear to see, but it looks to me like they do eventually intersect somewhere up here. That blue graph is opening or increasing faster than the red graph is. Because the x value is within, we can actually still find the intersect. So second, trace, option number 5, and then there's only 2 curves. So first curve, second curve, the guess doesn't matter. And it gives me my solution at 2.140, blah, blah, blah. When I take that onto the home screen, we see that we did get exactly the same thing. So very, very verifiable via your graphing calculator. And just so that we do have that in the notes, I'm just going to write underneath that x is equal to 2.14 when we round to the nearest hundredth. All right, that is definitely I would say the hard section of 8.4. is solving equations using logarithms. It requires a ton of practice, which students typically don't like. All right, a couple examples left to finish off 8.4.